All right, so we've seen what happens in the mouth, in the teeth, the salivary glands, and the fact that the saliva is sort of the first stage of chemical breakdown of the food. We've got the physical action of teeth that are chewing things up. So if we want to begin by looking at just to summarize, the mouth, right, which contains the teeth. And of course, the teeth are physical digestion, the grinding and chewing, breaking down of food particles into smaller food particles, right? So the breaking down here is just size. And then, of course, we also have saliva, which contains enzymes. Again, just reviewing from last time. And these enzymes, of course, are breaking down. Primarily, they break down starch. Enzymes for starch breakdown. And that enzyme is called amylase, just in case you want to, with an E on the end. Enzymes always or usually end with this ase. So when you see ase on the end of things, there's a good chance you're talking about some kind of protein enzyme that, and we say that the enzymes for breaking down of starch, remember the enzyme itself doesn't break it down. It allows for the biochemical reaction to break it down to take place. Enzymes are catalysts that help reactions proceed. Right? They essentially lower the amount of energy that's needed to make a reaction start, which makes it more easy then to proceed. So the enzymes, but we often shortcut that and we say, the enzymes break down starch, but in fact they are catalysts that aid in the breakdown or enable the breakdown reactions to actually happen. I see I spelled saliva there weirdly, that's an A, saliva. And of course the other function of saliva, besides the enzymes, is to moisten the food. It's basically going to moisten the food particle and make it liquid. Very hard to swallow something that's dry. If you've ever eaten like a cracker, well, you can't really swallow it until it's kind of mixed up with saliva and it becomes wet and easily able to slide down through the rest of the system. Okay? All right. So we have this chunk of food after the mouth. After it's been all moistened and filled with saliva, we have a name for it, believe it or not. The chunk of stuff that you swallow is called a bolus of food. So at this point it's wet, it's chewed up, it has sort of the consistency of something like oatmeal, right? And it's or a little bit rougher depending on what you've eaten, right? If it's a chunk of meat, it's basically it's small pieces of meat, a little bit of saliva. That's called a bolus of food. So the next place that it's going to go is into the pharynx. Now the pharynx is another word for the throat, right? And really the throat is it doesn't have a specific function in terms of digesting food. It's more or less a stop along the way. It's kind of like when you walk into a big building and there's usually like an entryway, a foyer, or a large atrium where you walk in and there's the information desk and something like that, or a big hotel where the concierge is and you go in and register and check into your room. So the throat is sort of like a meeting place and a sort of like an entryway to the system. And so it's the meeting place of several things. The meeting place, I'm going to put that in quotes, for obviously the mouth. So anything coming through the mouth enters into the pharynx. The nose is connected from the back of the mouth to the pharynx, as we saw in some of our pictures. Even the ears have a tiny tube that drains into the pharynx so that any mucus or infection in the inner ear can be drained. And even the eyes connect to the pharynx. There's actually videos of people who've developed a strange ability where they can put something like milk in their mouth and then they can make it squirt out of their eye. You can Google that, it's pretty weird. But again, I mean, that's not normally what we do, but there is a connection. So it's the meeting place of all of these things. So because of that, the throat is often a place where we find things that we don't want in our bodies, like germs, right? They get in through our eyes, through our nose, not so much through our ears because our eardrum sort of seals it off from the outside world, but things can get in here. So sore throats are often a cause of, something that's gotten in through any one of these places. So that's the pharynx. Then, of course, the pharynx leads us into the esophagus, which is the tube heading down to the stomach. Esophagus. Now, this tube is, it's not like the trachea, which has hard rings of cartilage to keep it rigid. The esophagus can't work if it's rigid. It has to be soft and flexible. So it's a soft, flexible, muscular tube. It's lined with muscles, smooth muscles. And those muscles allow it to squeeze in sort of a rhythmic way so that it can literally push food down. We often think that, because we usually eat standing upright, well, if you swallow something, it just gravity drops it down into your stomach. But that's not what happens. It gets squeezed down gently through this contraction of the esophagus. Think about a dog. Well, a dog is sort of a sideways animal. So when they swallow, something has to push the food towards the stomach sideways. And it's the motion of this esophagus. We can look at this. If I go back to my YouTube here, I thought I had one. I guess I'll have to get a new one. Let me go back to YouTube here, and let me just type in here something about peristalsis, because that's what this motion is called. And there's some really cool videos. Peri, I've got to spell it right. There. And we'll be able to see sort of what this looks like. There was one here I saw where they swallowed a pill camera, this one. So we'll just watch a little bit of it. We don't need sound. But you can see here, this is sort of looking straight down the esophagus. So somebody's swallowed a little pill, artificial pill that has a camera built into it, and it goes down and it'll film it. So what you're seeing here is sort of the last little wave of contractions that's gone by. And what you'll notice is out here on the outside, out in this region, around here, you're going to see a new contraction start, and you can imagine that it's kind of like a wave that just kind of ripples into the picture down towards the bottom of the esophagus. So we'll just watch that play out. Give it a second. You'll see it start to contract around where I've drawn that black line on the outside. Okay, here it comes now. You can see it's contracting inward like this, right? And then it's kind of pushing as it contracts. The contraction goes down the tube and pushes down. So anything that was in front of that contraction would now be pushed further down. And then, of course, it relaxes and opens up again. And then the whole thing starts again. Here comes another one, another wave. And they just keep doing that slow all the way down the esophagus until the food is pushed all the way down to the stomach. So you can see how it's smooth. It's got muscles, right? Let me see if I can find another video that has a picture of it sort of from the outside. So we can see it from the outside. If we go back here, I think this one, let's have a look at this one. I have to bump it up here to here. Okay. So now this is looking at the outside. This is actually in an intestine. This is not an esophagus, right? Let me just quickly erase those, erase that. Okay. So this is in, oh, it didn't work. Oh, well. This is in the intestine, which does the same thing. This is, I think, the colon, actually, or maybe the small intestine. Anyway, you can see it, as it's sort of like doing this pushy thing. You can kind of, it's kind of a blurry picture, but that's the idea anyway. Okay, so that's this peristalsis. So let's just pause that. Go back here to our... So soft, flexible, muscular tube. Okay, contractions of the esophagus occur in a, let's call it, whoops, let's spell that right, a rhythmic pattern. A rhythmic pattern. And I'll put in brackets peristalsis. That's what it's called, peristalsis. That moves food along. I'm going to put moves the bolus along. Remember, that's what we called it, the bolus of gross food that we've just swallowed. Moves the bolus along towards the stomach. And we'll see peristalsis again in the intestines. It's the same process that pushes it through the intestines. Okay? So the esophagus is basically just a connecting tube. And then, of course, we get to the stomach. All right, so the stomach is the next thing along the way. And of course, we also talked about the fact that the stomach has little muscular rings at the top and the bottom of it. So if we sort of draw a little esophagus here, and then it opens up into the stomach is sort of a pouch. Whoops, let me fix that bottom part there. The stomach has a little sort of, it's like a pouch. And then this would be the small intestine here. And the first thing we want to talk about is the fact that right here at the top, there's a ring of muscle, a sphincter muscle, that closes, much like your finger and your thumb, if you just squeeze like that. It closes off this tube. And there's also one down here at the bottom, so that the stomach can be closed or sealed. So once the food slips down into the stomach, like this, it comes down in here, this little valve, right, which we call a sphincter muscle, this one is called the cardiac sphincter, remember from our picture? It's called that because it happens to be near the heart, but it has nothing to do with the heart or anything like that. It's just its location that gives it that name. And then down here we have the pyloric sphincter at the bottom. And these little muscles, whoops, yeah, that's right. These little muscles are critically important because when the food hits the stomach, it has to stay there for a while, several hours, because a lot of work has to be done. So far, all we did is chew it up in pieces and add a little bit of that amylase from the saliva, which starts to break the starches down. But there's still lots of other big molecules that need some work, in particular those big protein molecules. Protein, remember, is a very large molecule. It takes a lot of time to break that down into smaller pieces. And so these, of course, will seal it off and keep the food in there for a while. Now, what's interesting is if you fill up your stomach too much, I'll just draw a little picture over here again. If your stomach can swell to hold on to large amounts of food. So after you've had a big meal, Thanksgiving dinner with turkey and stuffing and all the rest, your stomach may have swollen to maybe 2 or 3 times its regular size. Okay, it's about the size of your fist when you haven't eaten, but it can swell up, it can stretch. And when it stretches, that can sometimes put pressure on this little cardiac sphincter. So there's all this food that's pushing against the sphincter, and that can cause it to squeeze open. And if it squeezes open, then some of the stuff that's in your stomach, of course, remember, it includes these strong digestive juices, but also acid, hydrochloric acid, that can squeeze up into the esophagus through the forced open sphincter. And of course, when that happens, the acid can burn the sides of the esophagus. Now in your body, this happens right in the center of your chest, right? It's going up the esophagus from there. And it sort of feels like it's right around where your heart is. So we call that heartburn. But of course, it's nothing to do with your heart at all. Again, it's just because it feels like it's in that location. Heartburn, B-U-R-N. Heartburn is the condition where acids from the stomach are being forced up into the esophagus because the cardiac sphincter, has been forced open. Usually it's because the stomach is very distended and stretched from a large meal. Could also be you've eaten a meal, maybe it's not so large, but then you do some extreme activity and you're jumping and bouncing around, and it can force food to squeeze back up. Another thing that happens to people as you get older, everything gets a little bit weaker and doesn't work as well the older you get, right? So what happens to people like me, my age, is this little sphincter may not be quite as strong as it once was. And so at night, when you lay down, right? If you lay down at night, in the daytime, maybe the food only goes this high in the stomach and it's all full like this. But if you lay down, you turn it all sideways, the food is sort of sitting like on this side of the stomach now, and it puts pressure on this little sphincter, which now can squeeze open and let in the acid into the esophagus. And what's interesting is depending on which side you sleep on, it can be worse on one side or the other because it all depends on how the food is sitting in the stomach. So old folks like me sometimes will wake up in the middle of the night with a little bit of what actually happens is what's called acid reflux. Okay, so acid reflux is the condition where acid is going in, and the condition it causes is heartburn. So they're pretty much the same thing, right? Acid reflux or heartburn. There are solutions to that, of course. The obvious one is not to eat such big, heavy meals and to be careful about what you do after you eat a big meal. Or you can take antacid pills, which have chemicals that will neutralize the stomach acid. Remember in our chemistry we talked about neutralizing acids. So that neutralizes the acid, and then it doesn't hurt the esophagus so much. It's more neutral and not as much acidity. Unfortunately, though, the whole point of the stomach is to have acid to digest the food. So if this happens often enough to you, and you have this serious condition where you're getting this all the time, and you keep popping antacids, well, you're going to interfere with your digestion. So it's kind of a fine line. So suffering from heartburn occasionally is normal, but if you have an issue where you're suffering from heartburn all the time, you may have an underlying condition, and maybe something has to be done here, some kind of surgery or something to correct it. That's the point of the sphincters. And of course, at the bottom, the pyloric sphincter is holding everything in the stomach until it's ready to be passed on down into the small intestine. So let's write a couple of things about what's happening in the stomach. Ooh, jump around. First of all, the stomach does two kinds of digestion. It does a physical digestion, because the stomach, of course, is made of muscle, primarily. It has a thick muscular wall. That can contract. Again, sort of rhythmically, right? It just kind of squeezes and contracts and contracts and squeezes. And so it essentially sort of grinds up food. I'm not going to say, I don't know if it really grinds. The word we want here is, it doesn't rub anything against anything, like your teeth grind. Your stomach is more like it needs, like kneading dough. It needs the food, right? You know, if you've ever seen somebody working a big, large piece of dough to get the yeast mixed all through it, they just kind of squeeze it and squeeze it and squeeze it. It needs the food that's in the stomach. So that contractions, right? The other thing, of course, is we also have to do some more chemical digestion. So the stomach begins chemical digestion of a different kind of molecule. So what the stomach does is it has two major things that it adds. First of all, it secretes hydrochloric acid. Hydrochloric acid, HCl, right? And I'll put in, the pH here is around 3. So it's, I'm going to say 1 to 3. Depending on, how much you eat and what you eat and how much is secreted. The pH of your stomach is somewhere between 1 and 3, which is fairly acidic, which is why it would burn if it got out of your stomach and into the esophagus. And so that hydrochloric acid is going to start working on all kinds of molecules and breaking them apart. The other thing that the stomach secretes is something called pepsin. It's an enzyme. So it's a protein catalyst. It's called pepsin. And its job is to break down protein molecules. So remember, the saliva starts the starches going, breaking down some of the starches. The pepsin is for the breakdown of protein. Proteins are very large and they take a long time to break down. So this food is going to stay in the stomach, rolling around and being squeezed and sitting in this acid solution, breaking down a lot of the proteins and pretty much everything the hydrochloric acid breaks down. That acid is strong enough that it could dissolve metal, right? If you swallow a little piece of metal and it stays in your stomach, that acid can literally break it right down and dissolve it, which is pretty impressive. Now you might be wondering, why doesn't then this acid and this pepsin just destroy the stomach? How come the stomach isn't burning like the esophagus would if it leaked up through that cardiac sphincter? Well, the stomach has some protective measures. The stomach is lined with a layer of cells that produce a thick mucus. Basically just a thick, slimy goo, mucus. And the mucus serves as a protective layer to protect the stomach against its own acid. Its own acids, or acid and enzymes. Okay? Acids and enzymes. So it has this layer of mucus that it secretes. The other thing is these cells wear out very quickly. This lining is shed and renewed quite often. Regrown or renewed often in a matter of a few days. So even with the mucus, it does take a beating, right? It's a dangerous place, the stomach. It's a very harsh world down there. And so the body has to produce this mucus to protect it and then shed the lining and regenerate the lining quite often. Now, sometimes in the stomach, what can happen is something can interfere with the production of the mucus. So again, I'll draw you a picture of a little stomach here. There it is. Right? We'll put our little sphincters on the top and the bottom to remind us of them. And so now what I'll do is I'll take this blue and I'll draw this. This blue would be the mucus that's all coating inside the stomach to protect it. But sometimes you can develop a spot where the mucus gets thin or is not produced at all. And this can be for various reasons. The most common cause we've discovered now is bacterial infections in the stomach that can cause the mucus. So you see the spot right here, right, where the mucus is thin. That means that the acids of the stomach are going to start attacking. Oh, sorry, come back. Crazy smart board. It's not as smart as it thinks it is. Right here, all the acids now can rub against up here against the side of the stomach, and they can actually begin to digest it. And it'll get sore, and it'll bleed, and it'll become what we call an ulcer. If you get an ulcer in your stomach, you get a sore pain that's kind of gnawing away in there, and it's nasty, and it means that you've got an issue with the lining of your stomach. It's not working properly. Usually it's because of a bacterial infection, but the other thing that can cause it is stress. For some reason, one of the responses our body has to too much stress is that this can happen. In fact, in the old days, we thought that was the only cause. We often assumed if you had an ulcer, it was stress. You had to take it easy, too much stress. Now we've discovered that a lot of times it's actually a bacterial infection that's doing it. We know more about it now, but stress can be a factor. Stress basically affects everything in your body, and usually in a negative way if it's prolonged, right? We talked about, remember, the fight or flight and all of that. So that's what an ulcer is. An ulcer is in the stomach. An ulcer can actually happen anywhere. It's a medical term that refers to, a sort of a bleeding hole that's kind of raw and being sort of infected. You can have an ulcer on your skin, you can have an ulcer anywhere, but a stomach ulcer is usually what people talk about when they say, oh, I've got a terrible ulcer or whatever in my stomach. Okay, so now we see that the proteins are starting to be broken down. This takes quite a while. Food will stay in your stomach for several hours, grinding away. By the time it's done in here, it is basically now almost like really runny liquid. I'm trying to think of something that it might look like. Think about tomato soup. It's got no chunks in it. It's very runny. There's still lots of stuff in there, but it's really runny. There's a word we have to describe this stuff. Now that it's all sort of changed, the word is chyme. C-H-Y-M-E, chyme. Chyme is what we call the contents of the stomach. At this point. And it's very runny, liquidy. Okay. Now we're going to move past the pyloric sphincter into the small intestine. All right. So we'll draw a little line across here. Let's look at the small intestine. It's divided into 3 sections. Primarily, these sections just vary slightly in their function. We're not going to get into too much detail on this. When you do your grade 11 biology, you'll get more detail on all these sections and what they do. But the first one is called the duodenum. You've probably heard of that, maybe. The next one is called the ileum. And then the jejunum. Oops, let me spell that right. It's an E here. Jejunum. Now, we have the 3 parts of the small intestine. So the duodenum is first. It's the first section. So what's going to happen now is a number of things. This stuff has come in from the stomach, but again, guess what? It's got a lot of acid in it. And the intestines are not lined properly with the protective mucus. So one of the things that has to happen is that acid has to be neutralized very quickly. So in the small intestine, we'll just draw ourselves a little picture here. Here's our stomach. Okay, and there's the stomach. And now I'll just draw sort of a wiggly tube here. We've seen pictures of this, so we know what it sort of looks like, ... So there are some tubes that come from other organs. So in particular, the pancreas. So remember, another organ that's in the abdominal region, it's sort of folded, nested kind of right around where the intestines are, but I'm going to just put it over here, the pancreas. Okay? It's going to create or it's going to secrete a particular kind of material that's going to be sent right in here into the small intestine. And that's going to be what we call bicarbonate. So it makes a bicarbonate solution. Okay? You'll remember what that means, bicarbonate. So for instance, if you take carbonate, CO3, right, which has a 2- charge, remember from your chemistry, and then you put a hydrogen with it, that reduces the charge to a -1. That's bicarbonate, because the prefix bi usually means hydrogen. And then that would be an ion that, you could attach that to something like sodium with a crisscross. So, NaHCO3. This is called sodium bicarbonate. That's an H in the middle. But of course, when it's in a solution, the ions usually break apart and dissolve. So this bicarbonate ion would be floating around. And bicarbonate is a molecule, or it's an ion that can produce hydroxides in a solution, remember from chemistry, which can then react with acids to neutralize them. So this bicarbonate solution is secreted by the pancreas to get the pH back to closer to 7 so it doesn't burn the esophagus. I'm just going to erase that little bit of chemistry. The other thing the pancreas adds is more digestive enzymes. So plus, we'll put another arrow to show that it's adding two things. More digestive enzymes. And these enzymes break down everything. They are added for sugars. I guess I should say carbohydrates, because there could still be some starches, right? So the amylase got the process going, but it takes a long time, and so it's not like everything happens instantly. So there could still be carbs, carbohydrates, fats, or lipids, and proteins. So the pancreas is a very important organ for digestion because it adds another sort of cocktail of digestive enzymes to break things down even more. So even though we're past the stomach, there's still digesting going on in the duodenum. They're still breaking down. But it's at a molecular level now, right? All the chunks are gone, but we're now actually breaking apart molecules themselves into the smallest possible molecules that will eventually be small enough to pass right through the cell membranes and into our bloodstream. We'll get to that in a minute. But there's somebody else that also secretes something at this point. Okay, so maybe I'll put that, my picture doesn't have much room, so I'll draw him at the bottom. He's that funny brown, dark brown organ, right? And he looks something like this. He's kind of a great big fat organ like this. And it's of course your liver. Now his position is he sort of lives right over top of the intestines and the stomach. And we've seen his position. I'm drawing him down below just to sort of show that the food, remember, doesn't go through the liver. And it doesn't go through the pancreas. But these guys do secrete important enzymes. Now, the liver has attached underneath it this little gallbladder, right? This little sac. So the gallbladder is sort of associated with the liver, and it's another sort of guy we have to think about. But he's really just a storage place. So what the liver produces is something called bile. And this bile is going to be also secreted through tubes down into the duodenum, into the intestines. I'm going to write B-I-L-E here, bile. Bile, actually, here's what it does. It comes from the gallbladder. So the liver makes the bile and puts it in the gallbladder to store it until it's time for you to eat. And then the gallbladder secretes it into the intestine. Now, sometimes what can happen is the gall, that's the word for, gall is another word for bile. It's just an older word. And this bile has lots of chemicals in it. Bile salts, they're called. But sometimes these salts can crystallize. They can go from being dissolved to being little bits of solid material, kind of like a precipitate in a solution, but it's a slightly different thing. It's not a chemical reaction. It's just a crystallizing of these dissolved salts. And they can form tiny little rocks, which we call gallstones, rocks made of gall. And these gallstones can build up in the gallbladder, and they can block this tube, which sends the bile to the small intestine. So gallstones can be fairly serious. And sometimes people have to have their gallbladder completely taken out if the gallstones get too out of control. And what's funny is, or what's interesting, is that you can live without a gallbladder fairly normally. So the purpose of it, remember, is to store the bile. So you eat a big meal, you'll have lots of bile to put into there. The purpose of bile and the gall itself is primarily for digesting fats. Fats are also very large molecules, and this bile, what it does is it doesn't digest them, it emulsifies them. Emulsifies. So you'll remember that when you looked at fats, remember the membranes? We talked about membranes, and fats tend to clump together in water because remember they're made of those hydrophobic molecules with the tails that don't like the water. Remember that story? So fat tends to start off as little blobs, and they tend to stick together and make large blobs. So in this solution, this chyme coming out of the stomach, you're going to have lots of large blobs of fat, which makes them harder to digest. So emulsifying means you break the big blobs of fat into many little tiny blobs of fat, and you keep them from joining back together. Keep them apart. That's what emulsify means. It means keep the blobs of fat very small. So this gallbladder does that so that the enzymes can get in there all around, right? If it's a big ball, the enzymes can only get to the outside. But if it's many little small things, they can get all inside there and work much more fast, much more effectively. So that's what emulsify does. Now, if you don't have a gallbladder, because you had it taken out, what happens is instead of storing it and releasing it in bursts, you get more of a slow trickle of bile that just kind of goes straight through and right into here. Which is okay, because when you're ready to eat, that slow trickle is putting bile in. But the problem is if you have a big meal with lots of fat, the slow trickle might not be enough, right? So if you eat a lot of fatty foods, then what can happen is the fats will not be emulsified. They'll stay in big clumps. And then when they get further down the line, bacteria will start to attack them and eat them, and bacteria will create all kinds of gases and things, which gives you this extreme discomfort. And you get that bloated feeling, gas, and so on, right? So people without a gallbladder have to be a little more careful in terms of how they eat fatty foods. But for the most part, it's not like life-threatening or anything like that. So that's the gallbladder. It stores the bile, which is produced by the liver, whose job is to emulsify fats, to break them and keep them from clumping together into large chunks. Okay. And so those two organs are donating juice to the digestion process, enzymes. Now it flows through the intestine. Now this is where it gets really interesting. So we're gonna pause and take a little break. So the small intestine has a very interesting structure inside. When you look at it, it looks like it's just a tube like this. But if you were to blow up a section of this thing, sort of in a microscope and look at it, what you would see is that it actually is lined with little extensions all the way down like this. It looks something like this on the inside. The outside is relatively smooth. And these little finger-like extensions are sticking all up here like this into the inside of the intestine. And they are, they have a name, so let's label them. They're called villi or villi. So these little guys here, these little projections or finger-like extensions stick out. And what they do, of course, is they increase the surface area. So you can sort of get an idea. If I were to just draw this line, right, and you were to put people on the line, let's line up some people, you can only get so many because once you run out of room, that's it. But if you think about it over here, if you can put people all the way up here and all the way down there, you can fit a lot more people on that line, can't you? So that's what we mean sort of by the surface area. We can fit, or there's more space for stuff to be absorbed, because now we're at the point where things have broken down so much. The molecules are small enough that they can now be brought into the bloodstream. So this is what's happening in the small intestine. Now, if we blow up this one more time, if we take the edge of a villi or a vilum and we blow it up again, what we find is that one single villi has even smaller projections that are called microvilli. One single vilum has, so it would actually, that would look like this. Let me get a finer line to draw it. It has these very, very tiny extensions all over it. Okay, and that's just one of those bumps. So these are called microvilli because they're even smaller. So you've got this, which increases the surface area quite a bit, but then the surface of each of these little bumps is actually got little projections on it, which increases the surface area even more. So there's a tremendously large area for absorption of things to happen. And now the other thing that we have to understand is that when you get this small, okay, these purple lines I've drawn are sort of like what you would see in a microscope. So we're talking very small. These microvilli are tiny, tiny, tiny things you couldn't see with your own eye. And then if you think about one of these microvilli, okay, it's on here, the intestines are covered with blood vessels that are flowing in from the heart. And the blood vessels wind around these villi, and especially around these microvilli. So if we were to look at, a section here, and again, blow it up a little more, what we would see is that these tiny little projections have wrapped around them a network of capillaries, little blood vessels that branch all over. And again, they go from the heart and back to the heart. So we tend to change the color to show that blue is on its way back to the heart in this case, and the red came from the heart. So that's a capillary network. Capillary. That's an A in there. I better. Capillary network. So remember, this is almost microscopic. These capillaries, well, they pretty much are microscopic. They are about the size of one blood cell. Blood cells go through them single file, one at a time. And what that means is that any molecules now that are in the intestine are so small that they can move in here towards the villi, and then they can move, once they're in the villi, they can move very close into the microvilli, and once they're moving into here, they're small enough that they can move right through the membranes of these cells that make these tiny little structures. They either can slide right through, diffuse right through, or they can take the protein gates. They're small enough now to travel through the protein gates of these particular cells, which means they can be taken from the intestine through the gates, through the membranes of these cells that line the villi, the microvilli, and that line the capillaries. They're all made of cells, right? And they can be brought right inside to the bloodstream. So this is how the nutrients that we want end up into our blood. Remember we talked about you being like a donut? This is where things actually get inside of your body instead of being in the middle of the donut hole. So this is where things get absorbed. Now, most of the stuff that's absorbed is good for us. We want it. It's nutrients. It's tiny little building blocks that have been broken down from fats and proteins and carbohydrates, right? There are also other things that can squeeze in here. Things we've eaten that might not be good for us. Molecules that can cause us harm. Things that are poisonous or toxic to us. And so once this blood passes by the villi right here and it heads back, it doesn't go straight back to the heart. And it doesn't go all over the body because we have to make sure we get these things out of it. So usually it pools into larger and larger blood vessels, and then it's passed back through the liver. This time it's blood that's moving right through the liver. And what the liver will then do is it will extract some of the toxic things, and it will detoxify them. It'll break them down with its own special enzymes. So that's how we protect ourselves from things that are dangerous when we eat them. The liver will filter out the blood before we send it off with all its nutrients, because there might be a few things in there we don't want. So that's just sort of an aside that happens. And so this is how we get things into our bloodstream. At this point, remember, they are extremely tiny little bits and pieces of molecules, and they can travel right through the gates on the membranes of cells to get into the bloodstream. Okay? So this is how our nutrients are absorbed. Nutrients are absorbed into the bloodstream, so we can now use them. So that's a very important part of the intestine, the small intestine. Okay. So now what's left behind, if you absorb and take all the things you want, the only thing that's left is sort of the gunk that we really didn't want, right? And so what happens now is after you come wiggling out of the small intestine, you get to a spot where it opens up into what's called the cecum, and then there's the large intestine, which rolls up around the abdomen like this, comes down around the other side. There's a little bend in it, and then works its way towards the outside world. Well, we're almost at the end, right? So now let's talk a little bit about the large intestine. Well, the large intestine, it's dealing with the leftovers. Anything that we really wanted to absorb, we've already got. It's already been pulled in from the small intestine into our blood. So by this time, it's basically the leftovers that we don't want or we couldn't use. So what happens here is it's basically going to work its way through the intestine and out, but there's a process because there's something else still in this fluidy goo that our body would like. So two things happen here. One, the large intestine basically draws out water. And it draws the water back into our bloodstream. It too has capillaries all around it. Whenever we say something's going into the bloodstream, it's because there's capillaries nearby and it's pulling water into the bloodstream. All the way through, water is being pulled out, which makes that soupy, gooey liquid start to get a little more thicker and solid, right? And the reason we pull this water out is because a lot of juice went into digestion. If you think about it, we had to put in saliva. That's a juice. It takes water out of our bodies. Because remember, if you put it into the donut hole, that's outside your body. So digestion causes us to lose a lot of fluid. We put in saliva. We dump in the juices from the stomach, then the juices from the pancreas and the bile from the liver, right? All these juices are being put into this, and that means we've lost a lot of water. We'd like some of it back so we don't dehydrate. So the purpose of the large intestine, or the colon, one of its main purposes is to suck back some of the water that we have used for digestion, to save on water. So it reclaims water by pulling it back into the bloodstream. The other thing it does is, what's interesting here is there are bacteria living in here, tons of them. Now, normally we think of bacteria as being bad and causing, disease and being germs. But these bacteria are actually helpful bacteria. It's kind of more like what we call a symbiosis. Remember back in grade 9, you learned about animals that can sort of live and work together and help each other out. So these bacteria, they have the ability to break down things that our body could not. So they can break down some of the leftovers that we couldn't break down. And then they can break them into small enough little bits that they can be a sort of ride along with this water, like minerals and things, right? They can be reclaimed. So we can also get an advantage from this bacteria that lives inside of us when they break down whatever we couldn't. And we can reclaim some of that as it travels along with that water that's being reclaimed by the intestine. Now, there's a small trade-off here. It's not perfect because these bacteria, when they live in here, they use other biochemistry to break these things down. They use their own internal biochemical reactions, which produce some weird products. So we get sometimes gases and smells, right? And we all know where that's leading. And so part of the problem is in the colon, we do tend to get bacteria that produce stinky stuff and gas. And of course, it's not that big a deal because it normally just works its way right through the colon and out and, steady sort of every once in a while. Now, of course, sometimes it can get really bad because what happens is you get the bacteria producing too much gas and we get bloated and we feel that awful, stomachy, and we don't like that. But if it works normally, it's usually pretty reasonable. Now, the role of fiber. Fiber is important here because fiber is made of cellulose, right, which is the main component of cell walls in plants. So whenever we eat plants, we tend to eat a lot of cellulose. That's something we do not have enzymes to break down. So our stomach can't digest it, our intestines can't digest it, and it makes its way all the way through. It never gets absorbed, and it ends up here in the colon. But that's a good thing because, again, the colon is doing that peristalsis to push things through, and it's easier to push something that's got a little bit of form to it than something that's too sloshy or something that's too dried out and hard. When we're moving food through the colon, or not food anymore, the waste, when we're moving it through, if it takes too long to get it out, more and more water comes out and it'll dry up. It becomes very hard and dry, or drier. Or if it moves too fast, it'll come out very liquidy. And so different things can affect us to produce constipation and diarrhea and things like that. Typically, viruses can do it because they alter the cells of the colon and they change the way they're pulling the water. They affect them so that they can't pull as much water, and we usually get things like diarrhea from viruses. So the water stays in the colon instead of being pulled out because these viruses produce proteins that can actually alter the membranes of the cells and stop them from pulling the water out. Or if we don't have enough fiber in our diet, it's harder for the intestine to push things through, which means it stays in there longer and it gets dried out. And this, typically, eventually you work it out. It kind of is not a big deal. But in extreme cases of constipation, it can get stuck in there and not move for days or even weeks, which is pretty serious because it blocks up your whole system. And then you can have ruptures of the intestine, you can have infections and all kinds of problems. So typically, we eat fiber so that it'll keep the large intestine contents from getting too dry or too liquidy. That's the idea. Keeps them just right, soft and smooth and movable. Incidentally, what we call the stuff, of course, that comes out of here at this point, this is what we call our feces, right? And feces is mostly, because most of the stuff that's good has been taken out, it's mostly the bacteria, the dead bacteria cells, which is why it's gross. It's mostly bacteria that are growing in there. Bacteria live and die very fast. Every 20 minutes, they reproduce, they replicate, they grow, they die, they grow, they die. So we're getting rid of dead bacteria all the time. Mostly bacteria, and then remnants of undigested food particles that we just couldn't use. We couldn't use it, the bacteria couldn't use it, so it just comes through. But we've got most of what we want out of it. It's not 100% efficient, but we've done pretty well, right? And that's basically the idea. And of course, then the last parts are the rectum, where it's basically sort of the end of the large intestine, and it's basically a holding area so that we can regulate when we release these feces, so it's not too inconvenient. And then the anus, of course, is actually just a sphincter. I think it actually contains 2 sphincter muscles that basically opens and closes the final end of the picture. So the large intestine's role is to extract water back into the bloodstream, because we've invested so much liquid into this, we want it back. And also, it contains all these bacteria that can help digest things that we couldn't, and actually give us a few extra little nutrients that we can absorb along with that water that's being brought back in. So it's sort of like a final little bit more, just a little bit more. And we get as much as we can out of our digested food. So that's basically a rundown of the digestive system from start to finish and the different kinds of digestion. So it's important for you to know what's happening, sort of generally speaking, in each phase in terms of whether it's a physical or chemical digestion, and whether or not it involves, fluids that are being brought into the system, like from the pancreas and the liver, the gallbladder, or, what's actually going on in the intestines, the absorption of the food, and the villi, and the microvilli, and the capillaries, and how that basically fits together. So there's lots to remember there, lots to go over. You'll have to go through this several times to help your brain get accustomed to it.